So this video is going to be all about how to use external calibration. Now, in an external calibration scenario, what we have is we have an analyte stock solution that is at some high concentration of our known analyte. And this is prepared in a solvent similar to that which our unknown sample that has some other quantity of analyte present in it. This unknown sample of a similar solvent system to our analyte stock solution. Now we also are going to have to use some kind of a solvent blank. This solvent blank represents the solvent used in both our stock solution preparation and what is similar to our sample, but without any analyte present. Now for the rest of the calibration curve, we're going to make several standard solutions. Here I've indicated them as solution A, solution B, solution C, and these are made by mixing an amount of the stock solution of the analyte with the solvent. Now in this scenario, let's give some numbers here just so we can work through the math as we go. So let's say that this analyte stock solution has a concentration of 12 molar, the blank is at 0 molar, and the sample here is what we're trying to figure out, what is the concentration of this sample. Now when we make solution A, B, and C, we're going to mix certain volumes of the stock solution with the solvent blank, or with the same solvent used in the solvent blank, and now we'll get differing concentrations of solution A, solution B, and solution C. So for instance, for solution A, if we have 25 mils of the stock solution here, in 100 milliliters total volume, such as if we were to use a 100 ml volumetric flask, now we can calculate out what the concentration of solution A is. And we're going to do that using our trusty C1V1 equals C2V2 calculation. Now it's important when you're doing this calculation to make sure that you assign the C's and the V's appropriately. So on one side we have the concentration of our stock solution with the volume of the stock solution used. And on the other side we're using the final concentration of solution A, which is what we hope to find, and the total volume of solution A that we have prepared. Okay. If you swap the volumes or you swap the concentrations, now you're solving for a different variable and your numbers won't work out. Okay. Now if I plug in my numbers here and I solve for concentration of A, I get a value of 3 molar. And anytime you calculate anything, I want you to make sure that you do kind of a pause and a mental check and say, is this number actually reasonable? Right? If our concentration of our stock was 12 molar and our concentration of some kind of a diluted volume is 3 molar, that makes sense. We're going down in concentration. So always do that kind of double check. And so if we do solution B and solution C, and here we've used increasing amounts of analyte stock solution, when we do the same process to calculate out their concentrations, we get an increasing concentration from solution A to B to C, and all three are less than the stock solution. So it's a pretty good bet that we've done our calculations right. All right, so from here, now we need to get some kind of data from this. Now, the scenario I'm using here is, let's assume that our analyte is some kind of an iron cation, and we're going to do an electrochemical detection of this. So we're going to get some kind of an instrument response represented by I for each solution here. And these, because it's an electrochemical response, we're getting our units to be millivolts. Now you'll notice I have instrument response for the stock, each of the solutions we've made, as well as the blank. Now in many cases we assume the blank is 0, but this is not always the case, because whatever is in this solvent may be giving us some kind of a signal as well. And so taking a instrument response of the blank is going to help us account for anything in the solvent that might be otherwise giving us some kind of an instrument response at the start. Now I have all these numbers written out here. It's probably easier to view them as part of a graph. And so here I have my concentration in molar, my instrument response. Let's say these are all averages. If I've taken 3 instrument response and I get an average of this 1.025, there will be a standard deviation associated with that. And I also forgot to mention that I did take my instrument response of the sample itself. This also gets kind of the same average instrument response here of 0.406. Now, if I just start eyeballing this before I've even graphed or calculated anything, I would guess that this unknown is probably between the 3 and the 6, and probably closer to 6 molar than to 3, just based on it being a 0.4. So now I know kind of what number I expect to get just by eyeballing the numbers, and I can always go back and check my answer when we look at our final result. Okay, so the next step is to graph this. Now you'll notice I've graphed the concentration on the x-axis and the instrument response on the y-axis. And I've graphed these average values for each of our solvent blank and each of our standard solutions. Okay, I've also gone ahead and added a few things to this curve. First off, I added our x and y-axis labels to tell me what I'm looking at here. I've added a nice descriptive title that gives me more information than simply repeating what's already listed on the axes. Okay, I then took my plotted data and I added error bars, and these error bars represent the standard deviation of the instrument response, so I get a feel for, are these numbers very reproducible when I've made my graph? And the final thing I did was I added a trend line. Now this is a linear fit trend line, and I have not forced it to go through a 0, 0 intercept. So when I show the equation of the line, I am actually getting a y-intercept as well as a slope of the line. I've also added an r-squared value. This r-squared value will tell me something about how well this linear line fits the data. A value of exactly 1.000 to infinity will represent a perfectly linear line. Now this is not perfectly linear, although it is very close. So we have a number that is very close to a value of 1. The lower the number, the worse the fit is to a linear line. Okay. So now that I have this data from my calibration curve, what I'm going to do is I'm basically going to take my sample value here, this instrument response for the sample, and I know this would be a y on the y-axis at just over 4, and I'm going to calculate out then what it correlates to on the concentration using the equation of the line. Now because I'm calculating for the concentration, I have to rearrange the equation to solve for x, and then plug in my values for the y value, the slope of the line, or the intercept of the line b, and the intercept of the line b and the slope of the line m. Those numbers can be pulled from my equation of the line, or we can do this using a slope and intercept function in Excel itself. Now when you put this into the calculator, remember to add your parentheses around this numerator of the fraction to make sure that you don't end up with a calculator error along the way. And if I solve for all this, I get a value of 4.56, which when I looked at what I was going to get here, when I just eyeballed it, I said I'd between 3 and 6, and I guessed I was probably going to be closer to 6. But based on the fit of the line, and perhaps I didn't take into account that I wasn't going to go through a 0, 0 intercept, this does make sense, right? It's in the right ballpark of what we would expect. And if I look at my line, my graph here, if I have an instrument response of about 0.4, I should be getting something just under 5, and I am. So that's how you do external calibration calculations, where you take your known set of standards and a sample that you're interested in the concentration of, and ultimately get a concentration value for that unknown.